Bayesian view of learning. The Bayesian approach in training neural networks considers the parameters, namely connection weights Wi, as random variables drawn from a prior distribution P of Wi and computes the posterior probability given the data. P of W conditionally on X equals to P of X conditionally on W times P of W divided by P of X, where W is the vector of all weights of the network. The MAP estimate W hat is the mode of the posterior. W MAP hat equals to argument maxima taken among log of P of W conditionally on X, where the maxima is by choosing among all W. Taking the log of equation 11.34, we get that log of P of W conditional X is equals to log of P of X conditional W plus log of P of W plus some constant C. The first term on the right is the log likelihood, and the second is the log of the prior. If the weights are independent and the prior is taken as Gaussian, the normal distribution of 0 and 1/2 times lambda, then P of W is equals to pi of P of Wi, where the multiplication is chosen among all possible I, where P of Wi is equals to C times exponential of minus times Wi squared divided by 2 times 1/2 divided by lambda. The MAP estimate minimizes the augmented error function. E prime equals to E plus lambda times the square of the norm of W, where E is the usual classification or regression error, negative log likelihood. This augmented error is exactly error function we used in a weight decay equation 11.33. Using a large lambda assumes small variability in parameters, puts a larger force on them to be close to 0, and takes the prior more into account than the data. If lambda is small, then the allowed variability of the parameters is larger. This approach of removing unnecessary parameters is known as rich regression in statistics. This is another example of a regularization with a cost function, combining the fit to data and model complexity. But cost is defined as data misfit plus lambda times complexity. So the use of Bayesian estimation in training multi-layer perceptrons is treated in a McKay 1992 8b. We are going to talk about Bayesian estimation in more detail in chapter 14. Empirically, it has been seen that after training, most of the weights of a multi-layer perceptron are distributed normally around 0, justifying the use of weight decay, but this may not always be the case. Nowlan and Hinton, 1992, proposed the soft weight sharing where weights are drawn from a mixture of Gaussians, allowing them to form multiple clusters, not one. Also, these clusters may be centered anywhere and not necessarily at 0, and have variances that are modifiable. This changes the prior of equation 11.36 to a mixture of m, which is greater than or equals to 2 Gaussians. That the P of Wi is equals to summing of alpha j times Pj of Wi, where sigma is taken among all j starting from 1 to m, and where alpha j are the priors and the Pj of Wi, which is approximately by the normal distribution with parameters mj and sj squared, are the component Gaussians. M is set by the user, and alpha j, mj, sj are learned from data. Using such a prior and augmenting the error function with its log during training, the weights converge to decrease error and also are grouped automatically to increase the log prior.